So we are starting section 4.7, Stoichiometry of Precipitation Reactions. And for these kinds of problems, you'll have solutions, two solutions added together. Something will precipitate out, and all you need to do is stoichiometry for it. It's very simple. We'll just keep going. All right, so when you have a problem like this, you have to identify the actual reaction, what is insoluble, using your solubility rules, and use everything you know about stoichiometry. We're also going to use molarity. Okay, so here's an example problem. We want to find out how much lead 2 chloride will form when we mix these two solutions. And you should know, whenever you have two different chemicals, this one and this one, we're going to have to figure out the formula for this one. Whenever you have two different chemicals, you have a limiting reactant problem. So first, we've got to put our reactants together. Oops, there's our reactant, there's our other one. And figure out what's your balanced net ionic equation. So I'm going to pause this now. You're going to pause, and I'm going to reveal the balanced net ionic equation. But you're going to pause this and do that part yourself on your own paper. Try it. And there it is. There's our net ionic equation. So originally we had the lead nitrate, lead 2 nitrate, and aluminum chloride is AlCl3. Well, these are both soluble. We know that. Our two products would have been lead 2 chloride. We're already given that one. And then aluminum with nitrate, which we know is soluble. Just looking at these, you don't need to do your whole molecular equation because we know nitrates are always going to be soluble, so that's just going to be a spectator. We just care about the Pb2+. Aluminum chloride is soluble. Well, if we have Pb2+, it can't react with aluminum. You don't put two metals together. So it's got to react with our chloride ion, Cl-. And when we put those together, to make this all add up to 0, you need 2 chlorides. So we have to balance that reaction. Okay, now we have to determine the number of moles of each reactant ion. You're going to pause this, giving you some time to pause, because I'm not pausing. I'm just going to move this down and show you the solution. So remember, whenever you see molarity, rewrite this as moles over liters. Wherever you see molarity, cross out the molarity and rewrite it as moles per liter. So you would do that there and here, moles per liter. And you will use moles per liter as a conversion factor. Well, if you have liters and moles per liter, you should be able to get moles. So here we go. Okay, let's uncover a little bit more. Oop, there we go. A little bit more. There we go. Now we have our moles of the two chemicals. You should have done that already. You have to be a little careful with these because in a mole, liters times molarity gives you moles of the whole chemical. But in AlCl3, you have 3 Cl's for 1 AlCl3. So you have to be careful when you're calculating the moles. And here we have only 1 lead 2 in a mole of lead 2 nitrate. So it was just 1-to-1. Didn't make it very complicated. Now we have to figure out the limiting reactant. We can use our stoichiometric ratios. We can use, I like to start with the larger value, so I would use 1.2 moles chlorine over the 0.15 moles of lead 2, and it'll give me a number. If that number is larger than the ratio of 2 to 1, then I know that chloride, I have more chloride than I need. So let's see. You should pause this and try it yourself. Okay, so here we go. We have our 1.2 moles of chloride over 0.15 moles of lead 2. That's how many moles we had of each. That ratio is 8. And the mole ratio in the reaction is 2 over 1, which is 2. 8 is bigger than 2, so the ratio that I have is larger than the ratio in the reaction, which means I have more Cl than I need. If this number was smaller than 2, that would say I have less chloride than I need, and chloride would be limiting. But I have more chloride than I need because of this ratio here, being bigger than the ratio in the reaction. So chloride is in excess, lead 2 ion is limiting. So I can calculate the product that I'm going to make based on my limiting reactant. Go ahead and pause if you haven't already, and do that on your own, and I'm about to show you the solution. There we go. Okay, so we use our limiting reactant, the lead, moles to moles, using the reaction coefficients 1 to 1. And then I just go lead 2 chloride to grams using molar mass. And here we go. Here's our answer right there. That's how many grams of lead 2 chloride we would have. Now I've answered that question. I'm done with this part of the problem. That's all it asked me. But now I'm asking you to go a little farther. In the example above, determine the concentration of all ionic species in solution at the end of the reaction. So we've got some complex stuff happening here. We had nitrate spectators, we had aluminum ion spectators. Chloride was in excess, so some of it will be left over. We're going to have to figure out how much. The lead 2 was limiting, so what's its concentration going to be? That one's easy. 0. Lead 2 was limiting. Its concentration is 0. The ion that was used in excess is going to need to be calculated. We have to figure out how much should we start with, how much did we use. The difference is what's left over. We know this is how much we started with. We can get how much we used by converting the moles of lead 2 to moles of chloride using the reaction, the stoichiometric reaction coefficients. And then once we get the moles left over, we divide by the total volume of the 2 solutions added together to get molarity. Remember, we added 1.5 liters and 2 liters. We have 3.5 liters total mixed together. Okay, and I already mentioned this, I believe. Maybe I didn't, but here you go. Okay, so let's do the chloride. That's the hardest one. We had 1.2 moles of chloride ion right here. Now we have to calculate how much lead 2 is left. So you should how much chloride is used based on the amount of lead that reacted with the stoichiometric coefficients. You should actually just see it's going to be twice as much chloride as lead, so it's just going to double this. But pause it, do that on your own, and here is your solution. So the moles that we used, 0.30 moles used. So the moles of Cl minus chloride ion left over would be our initial minus how much we used. So we have 0.9 moles left over. We need to divide by the total volume. I did not do that correctly. I just fixed it. Okay, here we go. Oops, there we go. So I had made a mistake originally where I divided by 2.5. We had 1.5 to 2 liters. We have 3.5 liters total, not 2.5 liters total. So I've just fixed that. Even teachers make mistakes. Usually, well, hopefully, usually, we catch them. All right, so we have 0.26 molar chloride. Now for the spectator ions, you can pause this, figure it out yourself, figure out how many moles you started with, and divide by that 3.5 liters, because they're your spectators. They don't change from beginning to end. And here's your answers. There you go. So for the nitrate, you calculate how much nitrate, how many moles of nitrate you have. You have to be careful about that subscript 2 there. You divide your moles by your liters to get your molarity. Same thing with the aluminum. Now this stuff is all going to disappear in just a moment, but you should get it. Okay, so we need to draw a beaker, and we're going to fill the beaker correctly. Oh, wait, not that kind of a beaker. We need a scientific beaker, not the Muppet character. Oh, what was I doing? What am I thinking? Okay, you had a beaker. Oops, let me close that up real quick. I wanted you to fill out what it should look like in that beaker. So given these concentrations, it's just about the ratio of the ions in there. And think about what solid you have in there. We had solid lead 2 chloride, and is the solid going to be floating, or does it drop to the bottom? So try to draw your own picture of this and think about it, and now I'll show you what I have. You should pause this while you draw your own picture. All right. The solid lead chloride is going to sink to the bottom of the beaker. And if we look at the ratios, these two, it's about a ratio of 1 to 2. And these two, it's about a ratio of 1 to 3, because 0.09 times 3 is 0.27. It doesn't have to be perfect. But I did these two about 1 to 2, and these two about 3 to 1. So that's how I got more chlorides than nitrates and more nitrates than aluminum ions, and you can see that from these ratios. And there is no lead 2 in there. Why isn't there any lead 2? Because it got all used up. It's all sitting in here. All right, Now you're going to try one on your own. So you're going to pause, and I'm going to put the solution up. If you get stuck, I will not show the whole solution. I'll show it piece by piece, but you should pause this and try it on your own. So first, I'm getting my reaction. Here's my net ionic equation. I know that the barium with phosphate is going to precipitate out because sodium with hydroxide, nothing's going to happen. Sodium's always soluble with other ions. Okay, so then we need the moles of barium and the moles of phosphate. I did a calculation. You should show your work on how you get these numbers if you're just copying the numbers down. Once you have your moles of each, you find your limiting reactant. Look at the mole ratio. I always like to start with the bigger number on top, so I'm going to do 0.2 over 0.15 and compare that to 2/3. If what I get is bigger than 2/3, I know that the phosphate, I have more than I need, because I need 2 of these to 3 of those. So let's see what happens. Okay. When I look at that ratio, 0.2 to 0.15, I get 1.33. That's greater than 2/3. Therefore, the phosphate is in excess. If this number was smaller than 2/3, the phosphate would be limiting. But here we find barium's limiting. Now we calculate the barium phosphate from the limiting reactant. There you go. Get our grams of limiting reactant. Now we're going to calculate the excess of everything. Okay, here's the solutions. You should try those on your own. But you can look. Okay, now we're going to try and figure out what is going on in that beaker. So we're just looking at the ratios. There is no barium left because it was limiting. Barium phosphate is going to end up on the bottom, and these will be left in approximately those ratios. And here's how I showed it in the picture. And you should pause and write your own picture first. Okay, there we go. The largest quantity is sodium. It's about twice as much as the hydroxide, and hydroxide is about 3 times as much as the phosphate. We're off a little bit here. It's 1 to 4 in here, not 1 to 3, but it's good enough. It's close enough. I wouldn't grade you on exact numbers unless I said it must be exact on a test or quiz. Okay, acid-base definition. All right, so we got some definitions here. So we have, what is this a definition of? This is a definition of a Bronsted-Lowry acid or base. Acids donate protons, bases accept protons, and protons are just H pluses. An acid-base reaction, another name for that is neutralization. Whoops, neutralization. And when we use a burette to analyze an unknown concentration of a solution, that's called a titration. And when the titrant reacts completely with the analyte, where nothing is limiting, that's the equivalence point. We add something to a titration to denote when the equivalence point, when we're near it, and that's called an indicator. Indicators change color to denote the equivalence point. And the moment where the indicator actually changes color is called the endpoint. Okay, just have to leave that there so I know where it is later. So we're going to do a sample problem. This is what a titration looks like. This is our burette. Burettes have stopcocks on them, and the stopcock opens up, and then the liquid from the burette will drip into our analyte, which is down here. So the titrant is in the burette, and whatever we're analyzing is down here, and the indicator goes in this beaker. Okay, so we do a titration, and we find out that we need 26.72 milliliters. We add that from the burette into 20 milliliters of a sulfuric acid solution. And we know that the concentration of the NaOH was 0.1 molar. Now what do we do when we see molar? We change it to moles per liter. Remember to always do that so that you remember to use that as a conversion factor. All right, so let's look at how we're going to solve this. First, we need a reaction. Go ahead, pause yourself and write the reaction. And I'm going to show it to you. What is happening? Now, It won't let me move this. There we go. There's our reaction. We don't need our net ionic equation, we need the balanced reaction. That gives us the stoichiometry between the sodium hydroxide and the sulfuric acid. Now we just do stoichiometry. If we have milliliters or liters and molarity, we can get moles. We go to moles using the reaction. And we're looking for molarity. We need moles per liter. Well, we know how many liters we have of H2SO4, and if we get the moles, we can get molarity. Okay, so pause to do this yourself, where I'm about to show you. Here's the molarity calculation. We got our moles, and we need to divide the moles of sulfuric acid by the liters to get the final molarity right here. You may remember this from last year. Losing electrons is oxidation, gaining electrons is reduction. And oxidation-reduction reactions, these are reactions where an electron, at least one electron, is transferred from one substance to another. Those would be the reactants. The reducing agent is the thing that gets oxidized because it is reducing something else if it gets oxidized. The oxidizing agent got reduced, and it does that by oxidizing somebody else. So it's the agent that oxidizes. But for Leo and Gur, here's Leo, the constellation Leo, and Leo the lion says Gur. My daughter pointed out this is misspelled, but for our purposes we want it GER. Gaining electrons is reduction. Alrighty. Assigning oxidation numbers. So to figure out who's gaining or who's losing electrons, we have to be able to assign oxidation numbers. If your oxidation number decreases or reduces, that's reduction. That means you're gaining electrons because you become more negative. So elements that become more negative are reduced. Elements that become more positive are oxidized. So in order to figure that out in a reaction, you first have to just assign oxidation numbers. So here's our rules. They're all written down for you already. And we're going to try these problems in the table. So aluminum right here. No charge. All free elements have an oxidation number of 0. So the aluminum here has an oxidation number of 0. Easy. You should pause this and try to do it on your own if you can. Aluminum plus 3. You can pause or follow along. Let's see, what's our rule? Our rule says monatomic ions. Monatomic ion, that's what this is. Have the oxidation number of their whatever the ion charge is, whoa, which is 3, so the aluminum is 3. This one gets tricky. Compounds, oxidation numbers have to add up to 0, so this whole thing must add up to 0. Well, Mg, we know that Mg is in the +2 column, so we know Mg is +2. And we have this rule that oxygen is -2, so we know that O is -2. All right, Smartboard's not working, so I can't write this, but it's like there was 2. The whole file is not working. Okay, Smartboard wasn't working. I'm going to have to just type in numbers. So we know magnesium is +2. We know oxygen is -2 by the rules up here. And then we have 3 + 2's, which is 6. We have 4 times 2 is 8 times -2. The total for the oxygens is -16, but each oxygen is still only -2. So total here is -16. That tells us the total on the phosphorus, since this whole thing has to add up to 0, the total on the phosphorus better be 10. And since I have 2 of those, and they must be totaling 10, each phosphorus must be 5. And there's our answers right there. Okay, so nitrogen, we know that, we don't know the nitrogen. We don't know anything. We know oxygen is -2. We know the total for the oxygen is -4. So -4 over there. Now for polyatomic ions, where's the information on polyatomic ions? There we go. Polyatomic ions, you have to add up to the charge of the polyatomic ion. So this total must add up to -1. So what do we add to -4 to get -1? We add 3. And we have only 1 nitrogen, so it must be 3. And there's our answers. Now note we put each element by itself, not the totals. So oxygen is not -4. That's the total of 2 oxygens. Each oxygen is only -2. Okay, I'm not going to go through the solution for these. Do these on your own, and I'm going to show you the answers in a moment. And there you go. This is the only tricky one, I think. O2, 2 minus. So oxygen, it can't be -2 because -2 times 2 is -4. -4 does not equal -2. This is a polyatomic ion. So the total here has to add up to -2, and I have 2 of them. So each of those has to be -1. All right, there you go.